Thanks everyone for coming. So real quick, I'm Vishal Prasad. I'm a backend engineer at Peloton, the cycling company. And this talk is about concurrency in Python. In particular, I want to talk about kind of the shared structure that, the commonalities between the various, cooperative multitasking libraries that we use in Python that are used frequently in lieu of, some multiprocessing or multi-threading or event-based alternatives. I kind of wanted to come to an understanding of that structure by building out kind of the basic, really basic elements of these libraries, just using, really elementary, but I think, relatively elegant ideas from basic Python. Okay, so so even before getting into things, I kind of want to set expectations and also kind of apologize in that this talk isn't very original. A lot of the ideas, this topic in general is kind of a perennial Python conference favorite. And there's been many good, very definitive talks given by very, august and senior Pythonistas like, David Beasley and Raymond Hedinger, and some others, even in this conference that I, owe a big, debt to in understanding all these things. But I find that it's still, when I was thinking about what to talk about at PyGotham, this really came very aggressively forward in my mind for two reasons, basically. One, even though it's kind of circulated material and kind of a well-trodden path, when I actually talk to engineers in industry, this material isn't very well known. When it comes to using, like gevent or, even legacy things like, stackless Python and async IO and so forth, what people tend to know are things like common use cases, how to scale out these systems, how to deal with pitfalls and limitations, but not really the internals and kind of the history of these things. So that's the first reason. So there's still an audience. And second of all, really, and this is kind of the more important one, the ideas are kind of inherently very beautiful and very compelling. I think but once you kind of get kind of a taste of them, at least kind of in my estimation, you get injected into this kind of idea, this space of ideas, which constitutes, I think, the philosophical underpinning of Python as a language, and really, gives you that flavor for the really elegant ideas that come in the design. And I hope I can convey some of that in this talk. Okay, so before kind of, again, triple, prefacing, before getting into the main material, I just want to kind of just situate ourselves. So first I want to talk a little bit about the global interpreter lock. So the GIL, is this mutex that exists in the CPython interpreter that basically prevents multiple bytecodes from being executed simultaneously, which will have this effect that within the context of a single process, you can't really take advantage of multiple cores. There's kind of a lot of griping about it, but actually kind of at this point in time, a lot of griping about people griping about it. We've kind of moved on. It's not, even though this kind of, takes away our ability to use true, thread-based parallelism, the type of very trivial thing that you'll find in most serious systems programming languages. It actually tends to not be too much of a loss in this world where we're waiting on file system reads and writes and database reads and writes and network reads and writes. Most of our systems tend to be I/O bound, and if we're scaling for compute, we have things like AWS, where the thing is you want to scale out the system horizontally, deal with that sort of traffic, and then when you have applications that really need that hard parallelism, you can still do it. You can actually still do it in Python, where if you write a C extension, you can have within the context of the C extension manually forcing the GIL to release on a thread, so you can do real parallelism and multi-threading in Python in a way. But it's relatively fine. but so in for Python threads, they're perfectly acceptable given that context, because they know that when they're blocked on I/O, they'll release the GIL for another thread to take up. So it's perfectly usable. But kind of the inherent nastiness of threads, just like hard to reason about. As time goes on, very hard to debug, not very elegant, and perhaps, it gives at least some motivation for thinking about different paradigms. And one of the paradigms that come up is this, coroutine-based concurrency that we're going to talk about. And to get into what coroutines are in Python, you need to talk a little bit about generators, because that's historically where it comes from in the context of this language. So just so I can get a sense, how many people here haven't really written their own generators or anything like that? Okay, all right, okay. So a pretty simple, very powerful concept. The generator functions just allow you to write your own iterators, and iterators are very good because they evaluate lazily. If you have this very long list of data, you don't have to pull all the data at once and store it in memory all at one time and do all the computation necessary. As you're iterating through some iterator, you just pull one object, do the computation required for that, and then just move on as required. Okay, so writing your own iterators via these generating functions is very simple. Here I just have this very dumb, redundant generator called myRange, which will just produce a range from 0 to n exclusive. And the key here is that we're not returning values, but we're rather using this yield statement. So basically, the key to understanding this is just that between calls on iterating on a generator, it'll retain the execution context of the generator, so that when you're calling next, it'll pick up where it left off. So we just run this, and first we produce 0. So we use this next function on the generator object that we produce, and then we just march down in this function until we hit a yield statement, and then we yield the value of I. And then next time we do that, we do all the necessary computation afterwards, this incrementation, and then keep on doing that all the way up until we get the stop iteration error. Okay, so very simple. The location that these generators are constantly used in is within the context of a for loop, where you can just iterate through the thing automatically without having this very silly kind of next function. And if you really need to pull it all in memory at once, you can just cast it to a list and have that representation too. So this would be the for loop, and then this is just the output for the list. So very, very simple. Obviously this is useful for things like database records, where you do these huge queries, but you want your cursor just to peel off the records one at a time. So this is some example code, just for Postgres. This is CyclePG2, the Postgres library for Python. You're just connecting to some database test. You create this cursor, and then you just execute this SQL statement that just blasts everything and just gets you all records. But then the point is that the cursor doesn't actually pull all these things into memory at once. You can just peel them off one by one. And so this is obviously indispensable and very useful. But the general and more interesting idea here is not just that you can iterate through a given generator, but that you can pipe them together. You can compose them. And this becomes, very good for, doing, pipelines of transformations on data, where you want, where at any given step you don't have to have the whole data there. You just, push, one value through this pipeline and then do all the transformations and get it out, and then do that over and over and over again. So this is just, a generator that composes on my range, where it's just a squared range. So we're just iterating over the range generator and then yielding up now the square of the values that we're receiving from there. So again, very obvious. You just get 0, 1, 4, 9, all the way through 81, and then you just get the stop iteration. Okay, obvious, trivial. But in the context of Python, and this is where it starts connecting to the actual subject of this talk, is that back in 2005 we had this interesting PEP 342 coroutines via enhanced generators. And just ignoring the coroutine part here, just looking at kind of what functionally happens. Let's see. Yeah, so this is kind of the key. So redefine yield to be an expression rather than a statement. the current yield statement will become a yield expression whose value is thrown away. Okay, so yield, no longer a statement, now is more generally an expression. What does this mean? In particular, one thing that it means is that now the yield expression can be on the right-hand side of an assignment. But more generally, what this allows us to happen is have generators that not just produce values, that just push them out one by one, but generators that receive values. Okay, so we're just kind of making this generalization, and for now, we'll just call a generator that receives a value a coroutine. There's a general concept of coroutine that we need to understand a little bit more about how this functions in order to figure out how those two connect. But for now, we'll just take it on faith that this is a coroutine. Okay, so now I'm just, sorry. So now I have this coroutine now that's doing essentially kind of the similar thing for the squared range, where it's now we have this spinning while loop, and again, just like before with the regular generators, between execution, calls to next, we'll retain our execution state. So this will be while true n equals yield. So this is utilizing yield as an expression now. So once we get to this point in the execution of the function, we'll be waiting on receiving a value into the function. Okay. Waiting on receiving a value, relatively simple, and then we'll print out the square of that value. Okay, but so there's some subtleties here. So when we instantiate the coroutine function, the first thing we need to do is kind of what's called priming the coroutine. This next squared will step us forward to this yield so that now we're ready to receive. If we don't do that, the coroutine doesn't really do anything. It's not accessible. But now once you've primed it, now it's ready to receive a value, and so now we can send it a value 3. So we'll just step forward here, do that, and then continue on in the while loop until it finds another yield statement to block on, and then again it's now it's back to where it was when it was primed, and so now it's ready to receive another value to send. So obviously you can write now pipelines that instead of, in the case of regular generators, push individual values through the pipeline. Now we can or rather, excuse me, now with these coroutines we can push values through the pipeline instead of with these composed generator functions, which are kind of pulling values by having these subroutines being these generators being subroutines of each other. Okay, so reversing kind of the order of this of the general pipeline we had before, writing them now with coroutines, we have this pipeline which will end up pushing a value from this range generating piece of the pipeline through a squared piecing pipe of the pipeline, and then eventually to a sync that just prints out the value. Okay, so let's do this in reverse order. So we have this print sync, very simple coroutine that will just receive a value and then print it out, and then that's that's the terminus of this pipeline. And then we have the squared pipe, which will take in the next coroutine because it needs to know what the next piece of the pipeline needs to send things through. So we'll just receive a value, square it, send it forward, and then this my range pipe will just, which will also have a yield statement, even though it's not receiving anything. We just have that there to demarcate, state between calls to next, and then we'll just send this generated list of values down the pipe, and we'll just instantiate these 3 pieces of the pipeline, connect them together, like so, and then we'll have this my range pipe that just iterates over 0 through 10 or 0 through 9, and then we just prime them. Okay, so then how does this look? Probably as you expect. So most importantly, we're iterating over the my range pipe, the first piece, the first component, pushing a value through rather than in the case of regular generators going through the sync and then demanding that values be pulled up. Okay. So that goes all the way through up to 81 and then stop iteration. Again, very very obvious. So how does this relate to but still okay, what does it mean? We just reversed the order of things. How is that actually important and meaningful at all? And why do we call this thing a coroutine? Well, so the idea of a coroutine is something we get is first really widely talked about by Knuth in the art of computer programming. I mean, also it's a wonderful thing that this talk and the last talk in this room were all about Knuth. Anyways, this is really the first statement we have of a subroutine. And so coroutine. Subroutines are a special case of more general programming components called coroutines. In contrast to the unsymmetric relationship between a main routine and a subroutine, there's a complete symmetry between coroutines, which call on each other. Okay, so I mean, this is the thing about it. So imagine, what he's saying with subroutines, like imagine just, a deeply recursive function that just, calls itself over and over and over again, and then it eventually bottoms out and then peels all the way back up. These are, subroutines with respect to each other, and they only have one entry point and one exit point, right? So they enter when you're going from one function to a recursive call, going into a subroutine, you're just entering into the top of the function, and then exiting back to the calling function. So if you were to think about kind of making this analogy to graphs within the context of subroutines, your programs are just trees, but with the generalized coroutines that can yield to each other and give to each other the control flow, we have just general undirected graphs where you can have more complicated, state machine-like structures, mutual recursions, things like that. And so how does it connect back? So looking at this, you can think of the regular generators as yielding single values, but we can think of these coroutines as not receiving values. And again, this is kind of like a paradigm shifting way. You have to reorient your thinking. You can think of it as yielding the control flow, okay, to a further coroutine. So what I mean by that is, so again, to step through an example. So repriming this stuff and then starting at the beginning. So we start with 0, calling next on my range pipe, where again, so at the beginning, before we call this next here, we have all these coroutines primed such that they're looking at their yield statements. The first thing on my range pipe we call next, we push out the value to the next coroutine in the pipeline, and then come back here to this yield statement. Now it's just spinning idle, not doing anything. It doesn't have any work to do. It can just give up control to whatever else wants to take it, and what's ready to take it, this next piece of the pipeline, which we've sent a value to, and now it's ready to go on until it does its computation into its next state. So instead of just pushing values forward, we can think of yielding control flow. And that's, once we understand that, we can start thinking about these coroutines as not being just functions, but thinking of them as being kind of like tasks in the context of like an operating system, like pseudo threads, independent execution contexts. And so we can take these ideas of coroutines and start thinking about ideas of cooperative multitasking. And I think that, and I hope the next example will make that a little bit clearer if that's confused. Sorry, did someone raise a hand? Okay, sorry, never mind. Okay, so right now so in this example we have the same pieces, 3 components of the coroutine pipe we saw before, but now we have 3 of these myRange pipes iterating over different values, 1, 3, and 5. We have all them primed, and now we're going to iterate through all 3 of these high-level coroutines. We can think of them now kind of like as tasks. In this round robin manner, where we put them onto this task, effectively this queue. We pop one off, and then push for whatever we popped off, one piece of work down the pipeline. And then if there's anything left to do, we put it back onto the pipeline. We put it back onto the queue. And we do that over and over again until we finished everything. So it's just this round robin execution where we'll do one piece of unit for the first pipe, second, third, over and over and over again until everything's done. Okay. So this really is just an iteration through these values. Let me just run that. Okay, so running it, so again we have 1, 3, and 5. So this is the first pipe. It does one piece of work and then it's finished. Then the 2 remaining ones do their work. And then we have, we go up to 1, then we go up to pushing 2, and then the second one finishes. Then we go up to pushing 3 and 4, and then the last one finishes. Okay, so this is just, kind of, very, very trivial, but they are cooperating. Okay, in the with the help of this, this iterator, this thing that's scheduling the iteration, and really, if we want to think about these coroutines as tasks, we can think of this iteration as a sort of scheduler. Okay, like if we're starting to think about this as an operating system. Okay. So first of all, is everything kind of up to this point relatively crystal? Okay, gotcha. Okay. So I'm just going to take that round robin code that we had up here and just put it into now a scheduler. Doing essentially the same thing, we just have this queue of tasks, and then we can add to the scheduler, which will just append it onto the queue. And then now we have this join function, which will just do this round robin iteration through all your tasks until all tasks you have in your queue are finished. It just blocks on doing that, and then it will return, well, it returns nothing, but returns all the work being done. Okay, so same exact thing, but just put into recast and renamed as a scheduler. And unsurprisingly, it's the same result. Okay, so this is kind of thing, very in this very approximate and rough manner, is kind of what the async IO event loop is, kind of what is happening under the hood with gevent, except obviously instead of having these arbitrary units of computation where these coroutines are just yielding to each other after doing a single bit of arbitrarily defined work, instead they'll yield to each other when they're waiting on IO. But we'll get to that later. We can start kind of building the architecture of what a lot of these coroutine concurrency libraries have by just building kind of very simple abstractions. So we could, for example, want tasks in the scheduler to be grouped together so that they're finished together synchronously. We could have pools, which is just a group with a finite cap on how many tasks you can put onto it. In the real world, you'd use these things for like connection pools where you can only have like 10,000 connections to your application, so you'll just keep on accepting connections into your pool until it fills up, and then you just balance everything that tries to come through until you do the work needed, and then space in the pool fills up. So this is kind of a basic example of how you'd might in this very kind of undisciplined way implement something like that. So it's just kind of the same thing as a scheduler where the pool itself will have a list of tasks and some maximum pool size, and then you'll just block appending at a certain point. And then the join function for this will just be similar to what we had for the scheduler. Pretty much exactly, but now then the scheduler, since we need to go to higher levels of abstraction, instead of taking just task, we'll take some sort of task unit, which could be like a group or a pool or whatever. And then now the join on this will just recursively call any joins we'll have on smaller data structures that comprise a task unit on the there's some like compound task data structure that's in the task queue. Okay, so just so this is a little bit clear. I'm sure it's not very abstract. We have again this similar sort of thing with the pipes. Now we have two range pipes of 3 and 3, and then 1 of 7, and we'll put these 2, 3 ranged pipes into a pool, and then add those to the pool, and then add the pool to the scheduler, so that those finish synchronously, and then unsurprisingly, the result will be something like this, where first of all the first 2 things that are put in the pool execute first, and then the last independent pipe will just get executed synchronously afterwards. Okay, so. Don't really need to go into the details of like adding more things. You'll just you could easily imagine more complicated things, like obviously schedulers will have like timeouts. Schedulers will have more dynamic groupings of tasks together in order to coordinate certain tasks having to done synchronously, some being done asynchronously. So we might want some task mapping that will allow us to group things more dynamically, having a timer, as I said. You can just build more and more and more things. And that will at least be a mirror of kind of the structure of these basic things. Again, so very simple. It doesn't require any advanced understanding of operating systems or systems programming to understand how this stuff works. Okay. And so in a real context, like in gevent forever, for example, the task the equivalent of the task will be this thing called a greenlit, which will just a pi greenlet is a range of C stack addresses that must be saved and restored. So these like greenlets exist independently of any scheduler, concept of a scheduler. This is kind of inheriting from an early idea of the tasklet in stackless Python, if anyone's used that or looked at that, where they had this tasklet idea, but those were like heavily kind of intertwined with the concept of a scheduler. These are kind of a more generalized concept that end up being kind of the core component of how gevent, for example, works. But that's really an aside. But okay, so this is cooperative multitasking, but it's not concurrency, because as I said earlier, we have all the coroutines seeding to each other after a trivial and basic, arbitrarily defined unit of work is finished, rather than, in particular, seeding to each other in I/O as Python threads do. Okay, so let's start looking at building that out. So the first thing, I have this very simple echo server. Hope is that legible? No. Wow. Let's see. How about that? Better. Yes. Okay. Okay. So it's a little bit socket programming. The details here are not very important if you're not familiar with this sort of thing. We just have the server create this read socket, and it'll be bound to some port that you're supplying, and all we'll do is just be this spinning while loop that will keep on waiting to accept sockets, and then we'll just read a kilobyte of data at a time. That's like the limit of the buffer, and keep on doing that over and over and over again until there's nothing more to read. Then close the connection, and then just spin forever. And so we'll have here just like two of these servers running, one on 1111 and one on 1112. And on the client side, we'll have, actually, let's see if I can put these side to side. I hope it's relatively legible. Okay, so we'll kind of need to side glance what's happening over here, but the details aren't very important. So on the client side, we'll just have these sockets. One that's going to connect to 1111, the other one connecting to 1112, and we'll just try to write these strings like task1, and then I just blow it up so that we have like roughly like a megabyte of data being sent through. And then task 2, okay? So sending to different servers, and then, sorry, the last thing is that we have this validation here at the bottom just to verify that the amount of data we intended to send is the same as the amount of data we did actually send. So we'll just go through that. And now, on the first server, it's just reading all that, printing it out. The echo server is working fine. And this exited out true, so we sent all we wanted to send. Okay, that's good. Same thing with the second one, Okay. The problem right now is just that if we want to execute these at the same time, right now on the client side, these are executing synchronously. So even though we're hitting two separate servers, there's no concurrency. Even though as this buffer for the socket is very small, but the amount of data we're sending through is very large. So inevitably, they're going to be waiting on I/O. So there's opportunities for them to see the context to each other, but right now they're not doing it. So to start, getting onto the road of making that a possibility, first we need to use non-blocking sockets. We had blocking sockets before, so that this socket.send call would just block hard here until everything here has been sent through. Now we're just going to, Python is very simple. C is very simple too. Just step blocking is 0. Now we're not waiting on the I/O to complete when we're sending things through this pipe. The problem now is we sent a very little amount of data until it blocked, and then we get false here. So we're not pushing through. So we just got the data over there. Just probably a kilobyte or so. So we need to make this a little bit better. We just have this while loop here. Actually, sorry about the kind of resolution thing. It's not great to read. But all we're missing on is comment. So okay, so we have this non-blocking socket, and now we're going to push as much data as we can, and then when we push that data, we'll just just cut that off from the amount of data we need to send, and keep on doing that over and over again. The key here is that we have this select call. And select, in Python, it's a library, but really in Unix, it just maps to the select system call. And what we're passing into it is a list of readable sockets, a list of writable sockets, and then select will tell us whether or not those sockets are free to do more I/O. And right now, we're not specifying any timeout, so this will block until all the sockets that we specify become free. Okay, so this solves our problem of having no partitioning of our data stream, so that we have nothing to work with the concurrency, but then also solves the fact that we're not pushing through all the data. So we'll just have that running, and just here, the length of data at the end should be the length of the data left to send. It's 0, so we sent everything we wanted to send. That's good. Okay. Now what we need to do in order to get actual concurrency is we need to wrap this into a coroutine so that when a given a writing coroutine is blocked, it can now yield control to another coroutine that's trying to do a similar sort of task. In order to do that, we also need to enhance kind of the scheduler we wrote before, modify it so that now it's a real concurrent scheduler instead of just this kind of toy example. Can actually move here, so maybe it's a little bit clearer. So the logic is actually very similar to the round-robin schedule we had before. The difference right now is that in addition to having tasks, we also have this other, essentially kind of, purgatory of tasks that are not ready to go. It's just this dictionary write waiting that will hold all the tasks that are waiting on writes, and the structure of the data will be the keys will be the file descriptors of the sockets that are waiting on I/O, and then the value will be the task, the coroutine that we want to schedule. And we just remove tasks from that queue into this, write waiting purgatory while they're waiting. And so, and is the same. Join now is much modified, or no, actually, only really 4 lines of modification. We're now, instead of just iterating while we have any tasks, we also want to check if we have anything on write waiting. And if we have some tasks, we pop a value off. And then now here is kind of the core difference. Instead of before with the round robin scheduler, we just had like next task. But now what we want is to have the coroutine yield up the file descriptor of the socket that's waiting, and it will only yield when it hits a blocking call to the socket it wants to write to. Okay, so once you get that file descriptor, then we keep that task removed from the task queue and then put it onto this write waiting data structure, and then we move on. And then in addition, we have this remaining step. So after doing a single unit of computation for a single coroutine, pushing some value down the analytical pipeline, now we'll also have this other step at the end. Excuse me, at the end, where we want to poll all the sockets in the write waiting structure and see if any of them freed up. So here, if we have anything in write waiting, we again call the select function, but now there is a difference where we're passing in the file descriptor of all the waiting sockets, and now we pass in this timeout of 0, which having that timeout, it means that now instead of blocking, we're just polling on those sockets, and so it'll return us these lists of reading and writable sockets that will contain the ones that are now free. Okay, so no blocking here, just answering a question, which sockets are free, and that's then once you have that, that the socket is freed, you just put it back into the task queue and remove it from write waiting. Again, pretty simple, right? but the kind of coroutine-based coordination comes in this client code here, where now we have send message instead of being just this one-off piece of script. Now it's actual a coroutine, and the only differences here really are one a trivial one, and that we're passing the message in. Fine, but now this spinning attempts to write. We'll just try to send what data we can, and then when we can't, when we hit a blocking I/O error, we yield the socket file descriptor. So this yield will hit to the scheduler right here. Okay, that's the only kind of coordination required. Now, just to kind of let's maybe get this a little bit clearer by just clearing up everything. And so now we have all the elements we need to have this client-side concurrency, and we'll just run this, have this going, and then we just have on the scheduler we have these two message coroutines that are just sending the same messages we were earlier, but now we have task 1 and then task 2, and then now so now they're behaving cooperatively, and they finish roughly at the same time. Okay, so now this is actual concurrency, and this is a very partial implementation. Obviously, we only did write sockets, but you want to do this for read sockets. And in addition, it's a general concept. We can have this also on the server side for handling the client connection. So you don't need to spin off separate threads necessarily to handle each client connection. You can have separate coroutines to do the same thing. Coroutines that exist in the context of some scheduler. Okay. So is that relatively transparent? Okay. So now what I wanted to kind of fit into this talk, and what is just don't have time to do, what I wanted to do is look into the internals of gevent and async IO once we hit this point, and look at what makes a real coroutine-based concurrency system robust. The unfortunate thing here is, don't have time to really do that in any detail at all. So instead, I just kind of want to kind of give a sense of the space right now. So even though this kind of scheduler is very similar to how the async IO event loop works, really kind of all this stuff is really getting slightly outmoded. In that this is really closer to how gevent works, and gevent is kind of like a Python 2 phenomenon a little bit. It's not really maintained and developed anymore with all these async ideas built into the language of Python 3 now with the pulling of async IO into the standard library. It's kind of, this sort of stuff is kind of going out. And so I don't really have much time to talk about async IO, but I just do kind of want to talk about, so this is in the documentation for async IO, the generator-based coroutines are now deprecated. So this whole stuff is now is going to be deprecated, and actually, will be removed by the time we get to Python 3.10. And so using the async IO, async and await kind of structures is really how you should be doing this stuff. But I think this it still retains much of the structure of how async IO works, and I think is more illustrative to kind of build it out from just raw coroutines. Okay, so that's pretty much all that I want to talk about in the main part of the talk, and I hope it becomes relatively clear how you can build all these systems quite trivially. But there's kind of two kind of ideas worth chewing and thinking about that I found. There's just kind of these two kind of sundry ideas that I thought were very interesting in the kind of coroutine space that I want to talk about. They don't really match. They're not really apropos of anything. One is this idea of mutual recursion. So with that quote from Knuth earlier, when he was talking about coroutines being this generalization of subroutines, and they can yield context to each other in all these interesting ways. What I've showed you so far is kind of the authoritarian version of coroutines, where there's a scheduler that kind of keeps all the coroutines in line, but like this sort of mad kind of spontaneous architectures that can come out from just coroutines working, collaboratively and like more democratically without this oversight, was not really touched on. And so coroutines, I think, can also be used to understand things like mutual recursion pretty well. And I just kind of want to illustrate that a little bit. So we have this, piece of bad code here for a very simple mutual recursion where you just have these two functions, and instead of recursively calling themselves, they just print out, whatever value they receive. Instead of just recursively calling themselves, they call each other. So like foo calls bar n+1, and bar calls foo n+2. This, if you read like theoretical computer science textbooks, you can see all sorts of interesting and beautiful problems that are best framed in this way. But if we try to run this in Python, obviously it doesn't work because we hit the maximum recursion depth limit, which like is default set to like 2,000 or 3,000. So we just keep on adding function calls onto the stack, and then it just says no more, and then just kicks you out. In most functional programming languages, they have things like tail call recursion, tail call optimization, which will allow you to work around this sort of thing. But we don't have that in Python because Guido says it's unPythonic. We can't really, as far as I know, get anything quite like of this succinct form to represent this general type of problem. But actually, kind of what I found, and this is kind of for people who have at least seen some async IO code, we kind of get this like very neat kind of async IO code that at least retains kind of the structure we want to represent a mutual recursion. Almost everything is the same structurally, except instead of having the like mutually recursive call, we have this asyncio.async call that puts the call to bar.n+1 onto the event loop, and then done on the bar side as well. And this works and goes on forever. And it is nice because, first of all, okay, obviously it's not actual recursion. It's really just iteration, because all they're doing in these recursive calls is adding onto the event loop these futures, these future calls to these mutual future calls. But the point is that I haven't seen any other place in Python where you kind of retain the structure. And having the structure is important because having the morphology to represent the questions that you really want allows you to build better abstractions and start orienting yourself towards different problems. If you were like an ML programmer, this stuff comes trivially. You do kind of mutual recursion, maybe not all the time, but at least like it's available to you. But without having kind of with trying to like recast this into an iterative, at least structure, you kind of dilute your own understanding, perhaps, of the domain space that you're investigating. So that's a nice thing. So a kind of way of using kind of these async concurrent libraries that isn't actually about concurrency, which I thought was like nice and a little like mind blowing when I saw it. And just the last thing is this little notion I found in this blog post by this guy, Eli Bendersi, just like a Google engineer who just has a nice blog. And he has this post called Coroutines as an Alternative to State Machines. And he kind of begins and ends with this like philosophical musing, this observation. Coroutines are to state machines what recursion is to stacks. And I really encourage you to kind of read through this post and kind of muse on what the meaning of this is, and then once you kind of get to that understanding, kind of try to backpropagate that understanding onto all the stuff that we now know about coroutines and concurrency, and see if that's kind of fruitful. So those are just like two little bits. Okay, so talk is done here. The last thing I need to do is just a bit of due diligence. Again, I'm an engineer at Peloton. We work on distributed systems in Python. Almost all of our stuff is in Python. If you're interested in that sort of thing, we're hiring at all levels. In particular, we need engineers on my team to help scale out our systems. So if you're interested in that, just shoot me an email at vishalprasad@onepeloton.com. Okay, so that's it.